7 now, that's right. So this week we're going to be doing a lot more derivations, and we're going to be talking about some of the strategies that we might actually use to be able to complete some of those derivations. And now that we've been sort of learning some of the tools on how to do derivations and the different rules, we can actually use derivations, strategies for derivations. Now that we have some of these tools, one of the things that we can use these tools for is to actually check for certain kinds of properties. So before we look into some of those properties like validity and inconsistency and equivalence, I'd like to say just a few things about derivations. So one of the things you'll recall when we did the truth tables and the semantics was we had this symbol, this double turnstile, and we said that whenever we have claims of this form, where actually, I just realized this should actually be gamma. That should be a set of sentences. So that's my bad. So here we said that Q is entailed by the set gamma, right? So this was a set, and this was some sentence. And this was what we called entailment. And this is a semantic notion here. What we're going to be working with now is what's called derivability. And when we want to say that some sentence is derived, we use a slightly different symbol, and we use the single turnstile here. And here we say that Q is derivable from the set gamma. So this is about derivability. Okay. So this is a claim about derivability. This is entailment, this is derivability. And one of the things that SD is good for is for checking for certain kinds of properties, namely the validity, equivalence, inconsistency, and whether or not a sentence is a theorem. And we'll go over some of the details of how to check that in the following videos. For now, what I want to do is just look at what it means to check for derivability claim. So let's start here. And I'm actually going to use examples from the text, not ones from the homework, but as I go over some of these, you'll hopefully be able to see some of the strategies that I'll be using that you can actually then use also for the homework assignment. So this is from number 1C, and the question is, what we're asked for, that is a terrible set theory, or set symbol. There we go. So what you're asked to check for is whether or not the following set of sentences, so the first member here is a conjunction of a material conditional, if K then L, and if L then K. So this set contains just one sentence, a big conjunction, and we're going to claim that this set, it is derivable from this set L if and only if K. So this is the derivability claim that we're going to check. Okay. So how do we do that? Well, to check this claim, we're going to assume the sentences in the set as our primary assumptions, and then our goal is going to try to be to derive this. So here, our first sentence is just going to be if K then L. And remember, this is just the same thing as and here, just a different kind of notation. It's a little bit easier for me to write when I'm using a mouse. Okay, so we make each of the members of our set, we make them individually a primary assumption, and since there was only one member here, this is our only primary assumption, and our goal is going to be L if and only if K. And so this last rule is going to be by biconditional introduction. and we're not quite sure what we need to use here, but we know that the main connective here is a biconditional, so we're going to have to use an introduction rule to be able to get this. So the first thing we can think of now is, given that this is the goal, we want to work backwards, right? We want to think, how do I get to introduce a biconditional? Well, if you remember what the rule for the biconditional is, what you do is you assume in the first case L, and you get K, and then you assume in the second case K to get L. And then you can do this biconditional introduction, right? So if I assumed L to get K, and I assumed in a separate auxiliary assumption K to get L, then I can introduce L if and only if K. So now let's work within one of these subderivations, and our goal here is to get K. And we notice that K is in two different spots, right? It's here, but it's also over here in the consequent. And usually when you find a sentence letter in one of the assumptions or in some sort of complex sentence, when those sentences are conditionals, you're usually aiming to get it out of the consequent position and then trying to build the antecedent. And here's basically what I mean. You notice in the subderivation I'm going to have L as one of my auxiliary assumptions. And that means that L combined with if L then K will allow me to actually get out K. So that's the sort of strategy that I have in my mind. I wouldn't try to go for K over here because K's the antecedent here, and so there's nothing I can really use here to help me get out K, because I mean that's my goal here, and in this case you'd be trying to get out L as your goal. So let's finish this one up. We know that this is a conjunction, right? So I can actually take out this conjunct L if K by using conjunction elimination. And don't forget, this is just another symbol for conjunction. And I need to cite line 1. Okay. And I should make sure to do this. I'm making this assumption for the purposes of biconditional introduction. And same thing down here. This was assumed for the purposes of biconditional introduction. Okay, so now that I have if L then K, I can actually just get K by using conditional elimination. And here I have to cite 2 lines, right? 2 and 3. So that completes this subderivation. Now I need to move down to the second subderivation here. And our goal is going to be very similar, or sorry, our strategy is going to be very similar to what we just had. We notice that we need to get L, right? This is the sub-goal in this subderivation. And we notice that it's up here. It's the consequent of this conditional as our primary assumption. So what we need to do is get that conditional out of this conjunction, and we can do that by using conjunction elimination. So we can go if K, then L, from line 1 using conjunction elimination. And then we just use conditional elimination to go get L. So we use, conditional elimination from lines 5 and 6. Okay, and then we can finish off our derivation, right? Because this is all we needed to do in order to be able to introduce the biconditional. We needed to have these 2 subderivations. We can now finish by just citing this first subderivation. So this will be 2 through 4. And then the second subderivation is 5 through 7. And that's it. That's what we have. Now, what we've basically done now is checked that indeed L, if and only if K, is derivable from this set. And this is, I guess, a side note. One of the things I won't be doing to you guys is giving you cases where it's not derivable. I think that would be a little bit unfair, at least at this stage of the game. So whenever you see one of these where there's a derivability claim, you can keep in mind that it is possible to actually get it. So not being able to find it doesn't mean that there is no derivation for it, at least for the purposes of the next week or so. Okay, so I'll stop it there, and I'll get into inconsistency and equivalence in the next videos and talk a little bit more about some other strategies you might use when you're doing your derivations.